6, here we go. Let's get cranking. Let's start with a quick review. Last Thursday, we got started in lesson 2. We're talking about how two things are related. How electricity is related to, go back to your title, one page, how electricity is related to magnetism. And today we're going to get started talking about it. Yesterday we learned what an Thursday we learned what the electric current was. It needs to be a closed path, which means the electricity needs to return wherever it came from. So I have a battery, and it's got to get back to that battery. We talked about the switch, like a light switch. A light switch disconnects wires. It breaks that closed circuit, guys. It says these things aren't touching anymore. We talked about the light bulb, a device that resists it or slows it down so that I can convert it to something that I should convert it to. And then we talked on Thursday, guys, of two types of circuits. We have a series and a parallel. Which one's in your house? A series circuit or a parallel circuit? A parallel, because if one bulb goes out, the rest stay on. So guys, sometimes we're tempted, if one goes out, they all go out. No, that's not how it works in our house. That's why we have a parallel circuit. Parallel circuit, more energy, prevents it, just takes more of wire. Today we're going to take on page 484 and we're going to take on page 485. Hopefully you got your little notes out there. I'm going to scroll my screen to it. Let's get started. Paragraph number 1 on it, on what a magnetic field is. Woo! Kennedy, paragraph 1, please.
Have you ever played with magnets? If you do, you probably know that each magnet has a north pole and a south pole.
Number 1. Continue on.
As you can see in the picture below, if you bring opposite poles of two magnets together, the magnets will attract or pull towards each other. If you bring similar poles together, the magnets will repel or push away from each other. The space around a magnet in which the magnet can
Exert.
a force on the other magnets is called the magnetic field. The field is strongest at the poles. Magnets attract or repel because of the magnetic field.
Okay, guys, we got a lot of blanks to fill in. I will make sure you got the blanks. Number 1, magnets have a
North and south.
good. If you bring opposite poles of the magnets together, the magnets will attract. So we have the saying lots of times in America, like, oh, opposites attract. Because we say we like different things, but we can still get along as human beings. We might hear that phrase, opposites attract, but it's definitely true when it comes to magnets. Opposite poles attract to each other. If you have number 3, if you bring similar poles together, the magnets will repel. They'll push away from each other, guys. Okay, now I don't know about you, but this is my world of magnets right here. Right? The little ones we put on our refrigerator. Am I going to be able to feel this? I'm trying to push them together, but they're repelling. I can't get them together. With these guys?
No.
No, these are too small, guys. Okay, so sometimes you can get it where, now these are a bad example because they're not, I can't get at the poles, but sometimes you get it where you're like, oh, I can kind of feel it a little bit, right? And then sometimes you're like, oh, they click right together. But these guys, they're so light magnets, you know, they can hold a piece of paper or a picture on the fridge and that's about all they can do, that we don't really necessarily understand it. Okay. Now we have number, I don't know, what am I up to in my notes? 5? 4. The space around a magnet in which the magnet can exert a force on other magnets is called the
Magnetic.
If I hold magnets 10 feet apart, can I feel them pull on each other?
No.
No, not normally. You're not inside the magnetic field, right? Okay, now we start getting really close, and all of a sudden, cling, they jump to each other. That's the magnetic field. Where's the magnetic field the strongest? Number 5. The field is strongest at the poles. So if you can get, in my mind, guys, a magnet that looks like the one on the bottom of page 484, you got that beautiful U-shaped one, that has very strong north and south pole, where all of a sudden you'll get within 3 inches and cling, they'll cling together, or you can start to feel that I'm trying to push north to north, and it's not working. That's the magnetic field, guys, okay? So you have number 6 then. Magnets either attract or they repel. So I'm trying to push north to north. They will repel. I'm trying to push north to south. They will attract because opposites attract, same repel. That's what we call the magnetic field that's going on. Now, I don't know about you, but I hear magnetic field and I start to think of like Star Wars. Oh, they got us in their traction beam and they're pulling us in and we can't get away. Yep. Okay? If you had a metal ship and I had a strong enough magnet, I would pull you in. Thinking that way, guys, if that helps. I don't know if it's the great analogy, but it's an analogy. Paragraph number 2, please. Soraya.
Not all materials can be separated. The movement of electrons, fields of an atom causes each atom to be slightly magnetic. For most materials, the magnetic fields face in every direction and cancel each other out. But in some materials, such as iron, coal, steel, and nickel, the magnetism of the atoms is stronger. The atoms are nothing but called domains. The magnetic domain is a large number of atoms with their magnetic fields pointing in the same direction.
Okay, guys, I don't know about you, but I fall into a temptation. So we got to get the first thing in our notes, which is number 7. Not all material can be magnetic. Now look at the picture over here, guys. The picture says this iron pot right here is not magnetized. And yet, what did Soraya just read? But in some materials, such as iron, cobalt, and nickel, the magnetism of atoms is strong. Well, I'm confused. Is iron magnetic or not?
No.
Yes.
And some of you are saying no, and some of you are saying right, and both of you are correct. Because can I make iron magnetic?
Yes.
Yes. Can I also make iron not magnetic?
Yes.
Yes. Okay, so you're going, whoa, how do we do that? Well, that's what we're going to learn about, guys. One of the things is why a material might or might not be magnetic. And that goes along this picture, guys. What's happening in this picture here? All the little magnets are pointing different directions. What do I really want it to do? All line up. When they all line up, they are forming what we call a magnetic domain. A magnetic domain is a large number of atoms with their fields all pointing the same direction. Let's make sure you have your notes from the top. 7, you said not all material can be. 8, the movement of electrons, guys. You have a name for that. The movement of electrons is called electricity. Okay, so they're preparing you for tomorrow, guys. They're actually preparing you to get to the, what are we talking about in this lesson? How electricity and magnetism are related. And both of those can produce each other because electrons, our movement, will give them, they'll make them slightly magnetic. So that was number 8 in your notes. Number 9 says, for most material, the magnetic field faces in every direction, and therefore what happens? They cancel each other out. So guys, that's in the middle here. If I'm going in every direction, we cancel each other out because it's not a strong magnetic field. That leads you to number 10. In some material, the magnetism is stronger. Why? The atoms line up in groups that are called domains. 11, your definition. A magnetic domain is a large number of atoms with their magnetic field pointing in the same. If I'm in the same direction, I'm magnetic. If I'm in a different direction, I'm not magnetic. One of the ways we can make iron not magnetic, beat it with a hammer. So if I literally smash it with a hammer, it scatters the way the poles are pointing. If I rub it with a magnet, that magnet literally is like, line me up, and lines it up. Okay, so that's one of the things you can do to make a magnetic work better. Do you have a question? I'm ready, go for it.
Each magnetic domain is like a small magnet with a north and south pole. If the domains are pointing in different directions, the material is not exactly. Some materials can be made into magnets. They are placed in a field. Will line up with the field. The material will be in the magnet.
Okay, guys, so what they're really saying is, if I want to make it a magnet, I need to get in a magnetic field. In other words, sometimes using a magnet will take other material and make it magnetic to line those things up. So making sure your notes are good, you have a repeat. Number 1 is just like number 12. A small magnet will still have a
North and south.
north and south pole. Amen. If the domains are pointing in different directions, then you don't have a magnet because they cancel each other. And then number 14, some material can be made into magnets. If it's placed in the magnetic field, their domain will. So I got to get them all going the same direction, guys. That's what they're trying to show you with those 2 types of pictures. Okay, last paragraph on that page. Nyla.
What do you think would happen to a magnet if you broke it in half? Would you have a north pole magnet and a south pole magnet? If you break a magnet in half, you don't end up with a north pole magnet and a south pole magnet. The magnet domains still point in the same direction as the original magnet. You end up with 2 similar magnets, each having a north and south pole.
Okay, so guys, that's that picture at the bottom of the page. I break this magnet in half, and if you're like me, my brain was said, if I break north and south in half, I have north and I have south. What are they really saying? No, you don't. You have small north-south and small north-south. Number 15, is that what that was? Number 15. If you break a magnet in half, you don't end up with just one north magnet and one south magnet. You actually will get the same directions, so you'll end up with 2 smaller magnets. Fill in the second blank. Each or both. I don't care which one you put down. Whatever helps you to think to say, hey, I have 2 north-south magnets. Okay, guys, let's finish it up with your Earth is a magnet and what that means for us. Amaya, give us paragraph number 1, and I'll take Soraya at paragraph number 2.
All compass needles outline in north-south direction. Did you ever wonder why, since the 1600, the English
Physician?
physician William Gilbert suggested that the reason is because Earth acts like a giant magnet?
Imagine a giant ball magnet running through. Earth is surrounded by magnetic fields similar to the field around the ball magnet. Suppose the imaginary magnet bar was sitting near the night that Earth theoretically. So you can imagine how the magnetic force is starting inside of the push out in the first place. The force lines that go around to the North Pole points to Earth's magnetic north and south.
Okay, 2 things we got to get in there, guys. First of all, number 16. It says, all compass needles align in a north-south
Direction.
and then you have to know number 17, guys. The poles of the imaginary magnet, in other words, there's not a real magnet running through our Earth, but we do have a magnetic field running around our planet, are located near, but not.
Exactly.
So if I use a compass, guys, what they're saying, is it going to point me north?
No.
Yes, it's going to point me north. I'm going to start traveling north, and I'm going to walk this whole world. Will I stop on top of the North Pole?
No.
No. Will I be close?
No.
Yes, that's 17. You are near, but not exact, the north-south pole. Now, if you believe evolution, guys, you know what the geologists believe about our magnetic field? Every so many million years, the magnetic field actually switches. Like right now, a compass will point you north. What do they say? Oh, in half a million years, it's going to start to point
North.
south and flip completely around where the magnetic field is coming from. That's if you want to believe evolution on the things that are happening out there. Okay, guys, we got the blanks filled in. Sorry I ran out of time, and sorry the internet didn't work. I had a video to show you. We'll try to get to that video tomorrow. That'll hopefully help us understand the power of magnetism as it is going on.